Hello, everybody. Today we're going to be looking at a different proof for exponent 3. So this is based off of a proof I found on Quora. I had to fill in some details and solve some exercises, but I think we're going to go ahead and go for it. So let's recall the theorem. So Fermat's last theorem for exponent 3 says, suppose that you have three integers a, b, and c satisfying a cubed plus b cubed equals c cubed, then at least one of those three integers must be 0. So let's prove this. We'll start by considering the ring of Eisenstein integers r equals z adjoint omega, where omega is a primitive cube root of unity. So for example, if you like, you can think omega is e to the 2 pi I over 3. Okay. Because every root of unity has magnitude 1, omega bar has to be omega squared, so I'll let you check that. And also, omega squared plus omega plus 1 equals 0. The reason for that is that omega cubed minus 1 factors into omega minus 1 times omega squared plus omega plus 1. Okay, but omega cubed minus 1 is 0, and c is an integral domain, so one of these two factors has to be 0, and omega isn't 1 since it's a primitive cube root of unity, and so this factor has to be 0. Disclaimer, throughout this video, I'm teaching a Fermat's last theorem course in the fall, and so there are a lot of things in this specific video that I will be leaving as exercises because they're going to be exercises for my students, and I don't want them to find this video and solve them ahead of time. Or if I do, then at least they had to work on it themselves. Okay, so anyway, one consequence of this fact here is that the ring R actually just consists of elements of the form a plus b omega, where a and b are integers. The reason for that is that higher powers of omega, like omega squared, can be written in terms of lower powers using this expression. Okay, let's define a function, a norm we call it, capital N on the ring R, by what does it do? So it takes in an Eisenstein integer, a plus b omega, and it spits out the product of its Galois conjugates, essentially. So it spits out a plus b omega times a plus b omega bar, which if you FOIL this out and use this fact here, you just get a squared minus ab plus b squared. All right. Now, you can also write n of a plus b omega as a minus b over 2 all squared plus 3b squared over 4. And what this allows us to see, in tandem with this here, is that n of x is a non-negative integer for all x in R, because this is non-negative. Okay? Now, here's a couple exercises for you. Check that the norm is multiplicative. So for any x and y in R, n of xy is n of x times n of y. And also check that n of x equals 1 if and only if x is a unit in R. Okay. Once you have this fact, you can check that there are only 6 units in R. They are plus or minus 1, plus or minus omega, and plus or minus 1 plus omega. You can use this fact here along with this fact here to see this. That's an exercise for you. Okay. It's also a standard fact from introductory algebra sequence that R is a Euclidean domain, and so it must be a unique factorization domain. All right, we will not prove this. As a consequence, prime elements are the same as irreducible elements in R. Okay, that's another fact from algebra. So prime always implies irreducible, but if you're a UFD, then irreducible implies prime. Okay. You can also check using the multiplicativity of n that x in R is prime if n of x is prime, although the converse is false. Okay? The key to this proof is this specific element in R that we're going to call lambda, and it's 1 minus omega. You can check that its norm is 3, and so by this fact here, lambda must be prime in R. You can also check that lambda squared is associate to 3 in R, which means that lambda squared divides 3 and 3 divides lambda squared in R. In other words, they differ by a unit. Okay, so try to prove that yourself. I know that's going to get annoying, but again, like I can't solve all these little preliminary exercises for the sake of my course this fall. If you're going to go ahead and try to solve that, you can just use the fact that omega is actually a unit in R and that omega squared plus omega plus 1 equals 0. Okay, here are 4 additional facts we will need to continue. Again, these are exercises. The first fact, which is only really needed to prove the second fact, is that every x in R is congruent to -1, 0, or 1 mod lambda. The second fact is that for every x in Z, the integer x cubed is congruent to -1, 0, or 1 mod 9, although really what we need is analogously, if x is in R and lambda does not divide x, in other words, if x is 0 mod lambda, then x cubed is plus or minus 1 mod lambda to the fourth, also mod lambda cubed, and also mod lambda squared. Okay? 3, let x and y be in R, then x cubed plus y cubed factors into x plus y, x plus omega squared y. This is really just an exercise in foiling. Okay, and then for 4, assume that x and y in R are coprime. Then up to units, the only prime element of R which can possibly divide both x plus y and x plus omega y, so these two factors here, is lambda. And the same is true for any two of the three factors on this side. If you pick any two of them, the only prime in R that can divide both of those factors simultaneously is lambda. We're not saying it does divide them, we're just saying it's the only possible one that can divide them. Okay? Okay, I think we're ready to move on to the proof. Yeah. So we're going to prove a stronger statement. We're going to prove that for any unit u in R, the equation x cubed plus y cubed equals uz cubed not only has no non-trivial solutions over the integers, but has no non-trivial solutions over the ring R, which is of which Z is a subring. So this is a much stronger statement. Let's assume to the contrary that we have x, y, and z in R star, so non-trivial elements of R, such that x cubed plus y cubed equals uz cubed. By the usual argumentation, back from earlier in chapter 1, we can assume that x, y, and z are coprime in R. Now, if lambda does not divide x, y, or z in R, then since it does not divide u, because u is a unit and lambda is prime, so check that, every term in the Fermat equation x cubed plus y cubed equals uz cubed is plus or minus 1 mod lambda cubed. That's by the second numbered exercise above. Hence, we would have the following expression. We would have plus or minus 1 plus or minus 1, although the signs don't have to match, equals u z cubed, okay, mod lambda cubed, if we were to take this mod lambda cubed. Where did the negative, why isn't this plus or minus u? Well, plus or minus u is just a unit, right? So we can just call that u. One easily checks by brute force that none of the 6 units in R satisfy this equation. This amounts to checking 12 congruences because there are 2 per unit because of the 2 different signs that are possible. Okay, there are 6 units, 2 equations each. All of them are easy to check. Okay, so that's a contradiction. So lambda must divide one of x, y, or z. Now, these 3 numbers were assumed to be coprime in R, and lambda divides one of them, so it divides exactly one of them. And I claim that we can assume without loss of generality that lambda divides z. Why can we assume that? Well, suppose instead that lambda divides, say, x without loss of generality. The case where lambda divides y is the same as the case where lambda divides x by the symmetry of the Fermat equation. Okay, then if you rearrange the Fermat equation, you get y cubed plus u negative z all cubed equals negative x cubed. If you reduce this modulo lambda squared and use numbered exercise 2 above, you find that this equation has to look like plus or minus 1 plus or minus u equals, okay, lambda divides x, so this will just be 0 mod lambda squared. And again, you can just check by brute force because you know the 6 units in R. The only u's that satisfy this equation are u equal plus or minus 1. Okay, so that's another exercise for you. Okay, so then what does this read? It reads y cubed plus or minus z cubed equals negative x cubed. Okay, but then we can just proceed as in the case when lambda divides z. We have something cubed plus something cubed equals like a unit times something cubed. This is like our new z on the other side, or maybe if you like negative 1 is u and x is now z, and this is like our new x. Okay, so anyway, so you can assume lambda divides z. So assume that, so then lambda divides z, and lambda does not divide x or y, remember, because x, y, and z are coprime. Okay, so here's our equation, x cubed plus y cubed equals uz cubed. Let's consider it modulo lambda to the 4th. Again, by numbered exercise 2 above, you have plus or minus 1 plus or minus 1 is equivalent to uz cubed mod lambda to the 4th. Now, lambda does not divide 2 in R. You can check that. That's a very easy exercise. So the left-hand side of this equation here must be 0 mod lambda to the 4th because the only other options are that it's 2 or negative 2. But if it was 2 or negative 2, then lambda would divide 2 in R, but it doesn't. okay? So this is 0 mod lambda to the fourth. So this equation actually reads 0 equals uz cubed mod lambda to the fourth. What that tells you is that lambda has to divide this z here enough times to make z cubed divisible by lambda to the fourth. And in essence, the fact that uz cubed is 0 mod lambda to the fourth means lambda to the fourth divides uz cubed. But, you know, lambda is prime, so it can't divide u, so it has to divide, like all 4 of these copies of lambda have to divide z cubed. So lambda has to divide z enough times for z cubed to be divisible by lambda to the fourth. In particular, we find that not only does lambda divide z, lambda squared must divide z. Okay, so in summary, we have the following. We have the Fermat equation, x cubed plus y cubed equals uz cubed. We now know that not only does lambda divide z, but lambda squared divides z. And we know that lambda doesn't divide xy. In other words, it doesn't divide x or y. Okay? Now, let's use numbered exercise 3. We'll factor the Fermat equation on the left-hand side as x plus y times x plus omega y times x plus omega squared y, and that equals uz cubed. Recall, by numbered exercise 4, that up to units, the only prime that can divide more than one factor on this side here is lambda. So why don't we count how many times lambda divides this left-hand side? Let's introduce some notation to do that. For alpha and r, let's let v sub lambda of alpha denote the number of times that lambda divides alpha. So this is like the lambda-adic valuation of alpha. Now, we know that the lambda-adic v lambda z is bigger than or equal to 2, right? Because lambda squared divides z, excuse me. Okay, well, if v lambda z is bigger than or equal to 2, then v lambda z cubed is bigger than or equal to 6. Okay, so in other words, lambda divides z cubed at least 6 times. So in other words, lambda divides this side at least 6 times. And because lambda is prime, it has to divide, you know, one of these factors at least twice, right? In order for this side to be divisible by lambda 6 times. Without loss of generality, we're going to assume for the rest of the proof that x plus y is divisible by lambda squared. The other cases are nearly identical. I can say, okay, so this was a gap. You have to actually check this, but it's true. I've checked it. The other 2 cases are nearly identical to the proof I'm about to give. Okay, in fact, you really just have to change these first few lines. Okay, so again, for the rest of the proof, x plus y is divisible by at least lambda squared. Let's look at the other 2 factors, essentially. So let's observe that x plus omega y happens to be able to be written as x plus y, so that first factor, minus lambda y. Now, we're assuming that v lambda x plus y is bigger than or equal to 2, and we know that v lambda y is 1 because lambda doesn't divide y. So this guy has lambda-adic valuation at least 2. This guy has lambda-adic valuation 1. So this guy has to have lambda-adic valuation 1. So that's an easy kind of valuation exercise for you. What about the third term? The third term is x plus omega squared y. That can be written as omega times x plus omega y plus lambda x. This term has lambda-adic valuation 1, okay? And this term has lambda-adic valuation 1 because we just showed that it did, okay? So this term has to have lambda-adic valuation 1 as well. In summary, we have the following. V lambda x plus omega y and v lambda x plus omega squared y, so that's 2 of the 3 terms in the left-hand side of the Fermat equation. Those have lambda-adic valuation 1. Lambda divides them 1 time each. And then the other term, which is x plus y, has lambda-adic valuation, well, okay, it's whatever the lambda-adic valuation of this is, minus 1, right? So we have lambda dividing this once and this once. Then we have it dividing this term some number of times. So whatever that number of times is, minus 2 is the number of times lambda divides this. Well, what is the number of times that lambda divides this? It's 3 times v lambda z, right? So v lambda x plus y is 3v lambda z minus 2. Great. Now, by unique factorization, so R is a unique factorization domain. Apart from the powers of lambda, we just discovered dividing this expression here. So this is the factored version of the left-hand side of the Fermat equation. Each irreducible factor in this expression, okay, must be a cube up to units. So the reason for that is the product of these guys is a cube up to units. And so by unique factorization, once we divide out the lambdas, what's left, each of those terms, so basically each of these terms, once we get rid of the lambdas that divide them, must be a cube up to units. So that's another kind of algebra fact. Okay, it's analogous to the fact, in the standard integers, that if you have a product of two integers is a cube, so if a, b is like c cubed, and a and b are coprime, then a and b are cubes. Okay, if you've never seen that before, that's a consequence of the fundamental theorem of arithmetic, which is a basically unique factorization, right? Okay, so the same thing holds in R. Okay, so here's what we'll do. We'll let t be the number of times lambda divides x plus y. We still don't really exactly know what that is. It's just that we know that it's at least 2. Okay, then let's call a x plus y, let's call b x plus omega y, and let's call c x plus omega squared y, so these three terms here. What do we know now? We know each of these is a cube. We know each of these is a cube up to units after we divide out all the lambdas dividing it. So in other words, we can write x plus a, which is x plus y, as some unit, u1, times a cube in R, so we'll say z naught cubed, times lambda to the t, where t is the number of times lambda divides this, which that's what we called t up here. Okay, then x plus omega y, that's a unit times a cube. We'll call that cube x1 cubed, times how many times does lambda divide this? Once. We showed that up here. Right? And then similarly, c, which is x plus omega squared y, is a unit u3 times a cube, y1 cubed, times lambda, because the lambda-adic valuation of c is 1. Okay? And again, all of these ui's are units. You might wonder why these are called x1 and y1, and this is called z naught and not z1. That will become clear in a moment. Okay, now no primes other than lambda can divide 2 or more of a, b, and c. That was numbered exercise 4. So we see that x1, y1, and z naught are pairwise coprime. Okay, that's again because primes are the same as irreducibles in a UFD, so in particular in R. All right. So basically, these new numbers that we found in R, they're still coprime. Okay. And none of them is divisible by lambda because all the lambdas were sort of pulled out already in A, B, and C. There's no more lambdas dividing anything that's left over here, here, or here. All right. Now, an easy calculation using the fact that 1 plus omega squared is 0 shows that a plus b omega plus c omega squared equals 0. You just have to write it down. Okay, and so if you plug in what a, b, and c are into this equation, it reads the following. u1 z naught cubed lambda to the t plus omega u2 x1 cubed lambda plus omega squared u3 y1 cubed lambda equals 0. And you notice that because t is at least 2, you can cancel a lambda on from all three terms. And that now reads u1 z naught cubed lambda to the t minus 1 plus omega u2 x1 cubed plus omega squared u3 y1 cubed equals 0. Okay, so let's continue. I think I'm gonna have to keep this equation kind of in sight before I scroll all the way down. Now, this t minus 1 here, let's notice that that's, okay, what is that? That was, okay, I think t was 3v lambda z minus 2. So t minus 1 is 3v lambda z minus 3. Now that is positive because t was bigger than or equal to 2, and this is t minus 1. And it's also a multiple of 3, clearly. Okay, so in other words, t minus 1 is like 3s for some natural number s. Maybe I don't need this equation. Let's scroll down. So here's where z1 comes in finally. Let's let z1 be z naught lambda to the s. In other words, like here's lambda. You can write t minus 1 as 3s. So then what is this right here? It's like z naught lambda to the s cubed. Okay, so we're going to call this z1, essentially. Okay, so let z1 be z naught lambda to the s. Then again, recalling that omega and omega squared are units in R. I mean, omega squared is a unit because it's a product of units, right? Okay, I do need this equation. What does this read now? It reads, let's see. What does this read now? It reads u1 z1 cubed, okay? And then omega is a unit. So omega u2 can just be called like u2 prime, and then we can leave x1 cubed alone. And then omega squared's a unit. So this here, omega squared u3, can just be called u3 prime, and we can leave the y1 cubed alone. So here's what we have. we have u1 z1 cubed plus u2 prime x1 cubed plus u3 prime y1 cubed equals 0 for some units u1, u2 prime, and u3 prime in R. If you multiply this equation by the inverse of u2, which exists because u2 prime rather, because u2 prime is a unit, and you rearrange, this reads the following: x1 cubed plus vy1 cubed equals wz1 cubed for some units v and w in R. Look familiar? Now, lambda divides z1, right? So, if you reduce this equation modulo lambda squared, you get the following. Again, using numbered exercise 2 above. You get plus or minus 1 plus or minus v is equivalent to 0 mod lambda squared. Okay? We've already seen this exact equation before, and we saw that when this equation pops up, the only units in R that satisfy it are v equals plus or minus 1. So, if we replace y1 here by negative y1 if needed, just to make all the signs line up, we get the following. This turns into x cubed, again, plus or minus 1, but pick the sign correctly so that it's plus. We get x1 cubed plus y1 cubed equals, what was it? wz1 cubed. So x1 cubed plus y1 cubed equals wz1 cubed. Perfect. This is the exact equation that we started with, except there's a change. There's a possibly different unit in front of the z term on the right-hand side here. But more importantly, what is the lambda-adic valuation of z1? It's 1 less than the lambda-adic valuation of z. Why is that? Okay, well, remember, t was 3 v lambda z minus 2. In other words, t plus 2 was 3 v lambda z. And we also called the lambda-adic valuation of z1 s, where t minus 1 is 3s. And so if you combine these facts together, you get 3s plus 3, which is known to be 3 v lambda z. And you can cancel the 3's then to find that s plus 1 equals v lambda z, which is exactly what I'm claiming here. Okay, in other words, assuming there's a non-trivial solution to the Fermat equation over R, we can produce a new non-trivial solution whose z component has lambda-adic valuation exactly 1 less than the lambda-adic valuation of the z component we started with. That's a contradiction by infinite descent. In other words, there's 2 ways to view this. If you iterate this procedure over and over and over again, you get a contradiction by infinite descent. Because once we reach the stage, let's call it k, where the lambda-adic valuation of the z component of the non-trivial solution, we'll call it z sub k, is just 1, you have a contradiction because we proved at the outset that if you have such a solution and lambda divides the z component once, then it divides it at least twice. Lambda squared divides the z term whenever lambda does. That's a contradiction because v lambda zk is 1. So it'd have to be at least 2 for lambda squared to divide it. By the way, z does continue to only divide the z term at each stage because x1 and y1 had lambda-adic valuation 0 because x and y did. Okay, so there's one way of thinking about the contradiction. You can't keep shrinking the lambda-adic valuation of this guy 1 by 1 by 1 by 1 at each iteration of this procedure, or else you'll eventually not have lambda squared dividing it. Okay, another way of thinking about this is that we'll eventually reach a stage where lambda no longer divides the z term, which would be the k plus first stage. Okay. However, it never divides the x or y terms, and so if that happens, it doesn't divide the x or y or z term. But that's impossible because we showed at the outset in the proof that lambda has to divide at least one of the x, y, or z terms given a non-trivial solution to the Fermat equation of exponent 3 over R. Okay, so there, I think this proof is kind of much, much cleaner than the original proof, kind of the Euler proof. And there you go. We'll keep pressing on into chapter, what are we on, 13, beginning next video, looking more about the flat deformation functor. So thanks for watching, and I will see you then.